The k-means algorithm requires as one of its inputs k, the number of clusters you want it to find. But how do you decide how many clusters to use? Do you want 2 clusters or 3 clusters or 5 clusters or 10 clusters? Let's take a look. For a lot of clustering problems, the right value of k is truly ambiguous. If I were to show different people the same data set and ask, how many clusters do you see? There will definitely be people that will say, oh, it looks like there are 2 distinct clusters, and they would be right. And there would also be others that will see actually 4 distinct clusters, and they would also be right. Because clustering is an unsupervised learning algorithm, you're not given the, quote, right answers in the form of specific labels to try to replicate. And so there are a lot of applications where the data itself does not give a clear indicator for how many clusters there are in it. And I think it truly is ambiguous if this data has 2 or 4 or maybe 3 clusters. If you take, say, the red one here and the 2 blue ones here, say. If you look at the academic literature on k-means, there are a few techniques to try to automatically choose the number of clusters to use for a certain application. I'll briefly mention one here that you may see others refer to, although I have to say I personally do not use this method myself. But one way to try to choose the value of k is called the elbow method. And what that does is you would run k-means with a variety of values of k and plot the cost function or the distortion function j as a function of the number of clusters. What you find is that when you have very few clusters, say 1 cluster, the distortion function or the cost function j will be high. And as you increase the number of clusters, it will go down, maybe as follows. And if the curve looks like this, you say, well, it looks like the cost function is decreasing rapidly until we get to 3 clusters, but the decrease is more slowly after that. So let's choose k equals 3. And this is called an elbow, by the way, because think of it as analogous to that's your hand and that's your elbow over here. So plotting the cost function as a function of k, it could help you gain some insight. I personally hardly ever use the elbow method myself to choose the right number of clusters, because I think for a lot of applications, the right number of clusters is truly ambiguous. And you find that a lot of cost functions look like this, where it just decreases smoothly, and it doesn't have a clear elbow by which you could use to pick the value of k. By the way, one technique that does not work is to choose k so as to minimize the cost function j, because doing so would cause you to almost always just choose the largest possible value of k, because having more clusters will pretty much always reduce the cost function j. So choosing k to minimize the cost function j is not a good technique. So how do you choose the value of k in practice? Often you're running k-means in order to get clusters to use for some later or some downstream purpose. That is, you're going to take the clusters and do something with those clusters. So what I usually do, and what I recommend you do, is to evaluate k-means based on how well it performs for that later downstream purpose. Let me illustrate with the example of t-shirt sizing. One thing you could do is run k-means on this data set to find 3 clusters, in which case you may find clusters like that, and this would be how you size your small, medium, and large t-shirts. But how many t-shirt sizes should there be? Well, it's ambiguous. If you were to also run k-means with 5 clusters, you might get clusters that look like this, and this would let you size t-shirts according to extra small, small, medium, large, and extra large. And so both of these are completely valid and completely fine groupings of the data into clusters. But whether you want to use 3 clusters or 5 clusters can now be decided based on what makes sense for your t-shirt business. There's a trade-off between how well the t-shirts will fit, depending on whether you have 3 sizes or 5 sizes. But there will be extra costs as well associated with manufacturing and shipping 5 types of t-shirts instead of 3 different types of t-shirts. So what I would do in this case is to run k-means with k equals 3 and k equals 5, and then look at these 2 solutions to see, based on the trade-off between fit of t-shirt, where more sizes results in better fit, versus the extra cost of making more t-shirts, where making fewer t-shirts is simpler and less expensive, to try to decide what makes sense for the t-shirt business. When you get to the programming exercise, you also see there an application of k-means to image compression. This is actually one of the most fun visual examples of k-means. And there you see that there will be a trade-off between the quality of the compressed image, that is how good the image looks, versus how much you can compress the image to save the space. And in that programming exercise, you see that you can use that trade-off to maybe manually decide what's the best value of k based on how good you want the image to look versus how large you want the compressed image size to be. So that's it for the k-means clustering algorithm. Congrats on learning your first unsupervised learning algorithm. You now know not just how to do supervised learning, but also unsupervised learning. And I hope you also have fun with the practice lab. It's actually one of the most fun exercises I know of for k-means. And with that, we're ready to move on to our second unsupervised learning algorithm, which is anomaly detection. How do you look at a data set and find unusual or anomalous things in it? This turns out to be another one of the most commercially important applications of unsupervised learning. I've used this myself many times in many different applications. Let's go on to the next video to talk about anomaly detection.